Hello, we're going to be doing standard 2.3, which is on the compatibility of observables, and we're going to be doing problem 2.13 out of McIntyre. It states that for a spin 1 system, show by explicit matrix calculation that the spin component operators obey the commutation relations in this following equations in McIntyre. And I have these represented here, which is that Sx commuted with xy, this commutator is equal to IH bar times the SZ operator, and then we have Sy commuting with Sz. This relation is equal to IH bar times the Sx operator, and we have Sz, Sx is equal to IH bar times the Sy operator. And it can be noted really quickly that these commutation relations can be expressed more compactly with Levi-Civita. And here we have that Si, Sz, or Si, Sj is equal to IH bar Levi-Civita epsilon ijk times Sk. Now we're going to verify each of these relations in the order they are given above, and a lot of this is just messy matrix calculations. So first we have the commutator here with Sx and Sy is equal to h bar squared over 2, and this is because we have a h bar over root 2 from each of these two operators, and similarly here as follows. And then we have 0, 1, 0, 1, 0, 1, 0, 1, 0, this is the Sx operator, and 0, negative 1, 0, 0, negative I0, I0, negative I0, I0, and then we subtract the opposite product because this is Sx times Sy minus Sy times Sx. So we have this similar constant out front, but now we have the two matrices flipped. And if we take the matrix product of each of these two, we have the same constants, but now we have I0, negative I0, 0, 0, I0, negative I, and negative I0, negative I, 0, 0, 0, I0, I. Now we subtract these matrices, we have the same constant out front times 2i, 0, 0, 0, 0, 0, 0, 0, negative 2i. We can pull out a 2i out of each of these easily. This 2 cancels, and then it's quickly noted that since the Sz operator can be represented as h bar times 1, 0, 0, 0, 0, 0, 0, 0, negative 1, this product here is equal to IH bar times Sz, which is exactly what we expected for this commutator. So this has been verified. Now for the next commutator, for the next commutation relation, we have now h bar squared over root 2, and this is because one of these is only an h bar, which is the Sc operator, which we note from above. And similarly here, and we have a similar matrix product twice here, and we multiply these matrices together. We have h bar squared over root 2 times 0, 0, 0, I0, I, 0, 0, 0. Then we subtract this other product, which is 0, negative I0, 0, 0, 0, 0, negative I0. We subtract these matrices. We have h bar squared over root 2 times 0, I0, I0, I, 0, I0. And here we can just pull out an I. This is the Sx operator. If we have an h bar, so we pull one of these h bars out and we have a similar setup as above, and we have IH bar times Sx as expected. And lastly, we can do the last commutation relation, and we take Sz commuting with Sx. We have h bar squared over root 2 once again, times 1, 0, 0, 0, 0, 0, 0, 0, negative 1, which is the Sz operator. We have 0, 1, 0, 1, 0, 1, 0, 1, 0, which is the Sx operator. We subtract the other product in the other way, and when we do the matrix products, we have h bar squared over root 2 times 0, 1, 0, 0, 0, 0, 0, negative 1, 0. Then we subtract h bar squared over root 2 times 0, 0, 0, 1, 0, negative 1, 0, 0, 0. And we get this matrix as followed. We have the same constant out front, but we have 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. And we know that we're supposed to have an I pulled out, so we have to do a little clever thing here and note that I squared is equal to negative 1. So if we pull an I out, we're going to have an I on the inside, and this is we're going to be left with I's here, negative I's here, and I's here, which is exactly what the S sub y operator looks as followed. So we have IH bar times Sy. And this means that we have verified these commutation relations for the spin 1 operators. And the reason that these operators are important is because commutation relations show if operators are compatible. If you take the measurement of one, you'll look at the other observable and you'll still be able to read the measurements. It's not going to collapse to a new measurement because you can observe them at the same time. You can take simultaneous measurements, which is really nice. And also, just to throw in a little bit of algebra that I learned from Ted's class, that the commutation relations are really important if we look at these matrices and their corresponding Lie groups and then look at the Lie algebras, because we know that a Lie algebra is completely determined by its commutation relations. And now that we know each of these, we can more easily work with this if we were to work with this part of quantum mechanics and look at more of the mathematical side of things. That'll be it. Thanks.